Okay. Thanks to the organizers for organizing this workshop and for the invitation. And okay, I want to tell you about some recent work on list-decodable codes. It's a joint work with three fantastic collaborators, Fernando, Tushant, and Shashank, and you'll also hear from Shashank very shortly. And let's get started. And please feel free to interrupt me at any point. So I'm sure everyone knows what a code is, but let me just set up notation. So we'll just think of codes as subsets of F2 to the n, or more generally FQ to the n, where Q is what I'll call the alphabet size, n is the block length of the code. And we'll think of distance between two code words as the fraction of positions in which they differ. So it will be a number between 0 and 1, and the distance of the code is the minimum distance of two distinct code words. Okay. And the problem of unique decoding a code is kind of makes sense for number of errors which is less than delta over 2, again in terms of fraction of errors less than delta over 2. So given some possible word x, let's say in FQ to the n, which is not necessarily a code word, but the goal is to find code words within distance delta over 2 of it, if there exist any. And by triangle inequality, there'll be at most one code word. The algorithmic problem of finding it is still highly non-trivial. But today we'll talk about list decoding, which is a problem where we're interested in radii, let's say rho, which are bigger than delta over 2. And now the question is, again, given an x, if there are code words within a ball of radius rho around it, again, in terms of fractional errors, find them, okay, and find all of them. And now there are two problems. There's a combinatorial question of how do I know this list is not exponentially large or something? I have to actually show that it's possible to even write them down. And then the non-trivial algorithmic problem still of finding them. There's a little bit of a catch. I mean, correctly state this problem, you have to make sure I'm not lying to you. So I could have a code where the distance is 0.9. I could just tell you the distance is 0.4. And then I have this great list decoding algorithm, which always outputs list of size 1. So, and also, I mean, I don't have to lie. There can be some like 2 or 3 code words which are just bad and everything else is great and so on. So you have to somehow make sure the distance is as large as possible to kind of compare ourselves to delta over 2 or sort of compare ourselves to the distance of the code. And this kind of bound is formalized in what's called the Singleton bound. It's in terms of the rate of the code, which is just log of the size of the code divided by log of the maximum number of words in your space, FQ to the n, or 1 over this is just a measure of the redundancy of the code. And the Singleton bound, as kind of Swastik proved last week, shows that the distance delta is at most 1 minus the rate. And the proof is just pigeonhole. Like if you look at this picture, then any two code words must differ somewhere in the first half of the picture because they need to differ in delta n positions and there's not enough room in the second half. Okay, so then we'll just kind of think of maximum distances as 1 minus r, and that's the kind of regime for which we'll try to think of delta and then list decoding questions and so on. Okay. Any questions so far? Okay, so now we have this optimal radius. Can we get there? Are there codes which do this? And again, there's this classical family of codes, Reed-Solomon codes, which, as Swastik said, like the best codes ever. And they actually achieve the Singleton bound, even in a non-asymptotic sense. They're just defined using polynomials. So you take a polynomial of degree k, evaluate it on n points. But you need alphabet size q to be large because you have to have n points in your field. In terms of list decoding, there is a slightly smaller bound than 1 minus r, which is 1 minus root r, known as the Johnson bound, where we know that the list size is always bounded. Okay. But algorithmically, it's still very non-trivial. In fact, some of the foundational works in algorithmic list decoding by Madhur and Venkat gave optimal list decoding algorithms or algorithm up to the Johnson bound for these Reed-Solomon codes. And I should say, today I'll be mostly interested in the combinatorial question. The algorithmic part, and Shashank will talk about it right after me, so you can sort of wait for his talk. So up to Johnson bound, the combinatorial question is kind of easy. And so let's go beyond the Johnson bound and see what you can say there. And we know quite a few things there also. So for random codes, we can decode them actually much beyond the Johnson bound. In fact, all the way up to very close to 1 minus r. But random codes, it's kind of hard to have a hope of an algorithm. So let's at least do combinatorial things where we have some hope. So the first codes which kind of go beyond the Johnson bound are the so-called correlated Reed-Solomon codes or by pervasive Bardi. And then there's this breakthrough construction of Venkat and Atirudra, which actually gets you all the way to 1 minus r up to an epsilon. And so formally the result is for every epsilon there exists an infinite family of codes which have list decoding radius at least this much. And this 1 minus r is sort of quantity known as list decoding capacity. That's the most we can hope to do in terms of list decoding, and we'll also see why. And so these codes are great. They get you all the way up to the maximum possible list decoding radius. And also, I should also say there are also other related algebraic constructions later, called multiplicity codes and so on. I'll not talk about them. Just for this sort of overview, I'll stick to folded Reed-Solomon code with apologies to some of the people who I might not be citing. Okay, so now we know the best possible radius. What about the size of the list? And this has also been fairly intensely studied over the last few years. So for folded Reed-Solomon, the original work of Venkat and Atirudra gave a list size bound which was something like n to the 1 over epsilon, where epsilon is this gap from 1 minus r, or gap from capacity. And then kind of a sequence of beautiful works improved this list size bound to be completely independent of n. It's only a function of epsilon, an exponential function of epsilon. And very recently, there have been kind of dramatic improvements further. So Shashank showed that the list size can be bounded by 1 over epsilon square, and an independent result of Chen and Zhang shows that it can actually be made 1 over epsilon, which I'll say is asymptotically optimal, and I'll kind of mention why. So we also know the best possible list decoding radius, the best possible list decoding like the size of the list, and then folded Reed-Solomon codes actually do this. Okay. All right, so that's roughly an overview of what we know. Seems pretty great. I mean, should we just go get coffee? Okay, so there are a couple of issues with this. So one, the first one is maybe a feature, not a bug. The algebra is really beautiful. So, but the other issue is that algebraic codes need large alphabet size. So in particular, for example, Reed-Solomon, we said it needs n, and folded Reed-Solomon, which I'm just going to call FRS, needs list size something like n to the 1 over epsilon square. The other issue is, as far as I know, they're not compatible with other nice properties we might want, like LDPC structure and so on. And I know Nick likes LDPC structure, so what am I going to tell Nick? And also, there's a slightly more philosophical question, if you indulge me. It's whether this kind of list decoding is a phenomenon that needs to rely on algebra, or sort of is this something more general? Should be more general because we know random codes do it, but so far these were the known constructions. Okay. So, as you might have guessed, the result I want to tell you about is a fairly elementary construction using expanders. In fact, it's not even a new construction. It's a 30-year-old construction, which we analyze. And we can show that it's list decodable again to the optimal radius, 1 minus r minus epsilon. Again, formally, for every epsilon, there is an infinite family of codes list decoding up to this radius. The list size is also asymptotically optimal. The alphabet is now a constant. It depends on epsilon, but not on n. It can also be made LDPC and so on. It's a flexible construction. And in fact, we get something even stronger than the list size bound. It's kind of arbitrarily close to what is called the generalized Singleton bound, which I'll describe in a minute. And this is also something that was true proved for folded Reed-Solomon code in this recent paper of Chen and Zhang that I said. Okay. So there's something a bit stronger than the optimal list size of 1 over epsilon. Okay. Any questions about the result, modulo the generalized Singleton thing, which I'll mention? Okay. So what is the generalized Singleton bound? Shockingly, it generalizes the Singleton bound. And a Singleton bound, which says that the distance is at most 1 minus r, can also be interpreted as saying, if I want a list of size at most 1, which is the unique decoding radius, the best I can do is 1 minus r divided by 2, because it's half the distance. And the generalized Singleton bound of Shangwan and Tammo, and independently Roth, says that if you want a list of size strictly less than k, then the best you can do in terms of radius is k minus 1 over k times this 1 minus r. So when you plug in k equals 2, you get the usual Singleton. And what we show, and what Chen and Zhang also show for folded Reed-Solomon, is that actually for any x, some arbitrary kind of center x, let's say, and for any k code words y1 to yk, the average distance of these code words from x is at least k minus 1 over k times 1 minus r. Okay. For this talk, Please ignore the epsilons. They're important, but yeah, they can be made arbitrarily small. Okay. So the average distance is at least k minus 1 over k times 1 minus r. So then if I look at a ball strictly smaller than this radius, all these k code words cannot be in the ball because their average distance is larger. So the list size is bounded by less. This list size is less than k. And when you take k equals order 1 over epsilon, you actually get arbitrarily close to 1 minus r minus epsilon kind of radius and list size order 1 over epsilon. So it implies the optimal list size, but it's stronger. Like it's also meaning for k equals like 5 or something. So, okay. Is the statement of the generalized singleton bound okay? Question? Yes. Okay, the second one is something which we show exists for these codes. Okay, the first one, yes, thank you. It's a feature of any code, and what we show is that there exist codes which match this bound. Okay. Other questions? I'm sorry? Y's are distinct code words. Thank you. That will be actually important. So yeah, this bound will be false if Y's are not distinct code words, and that will actually matter quite a bit. Yeah, I mean, like if I have 3 Y's to be the same, and if I take X to be one of them, then clearly this distance cannot even hold. Okay. All right. And I'll do this using expanders, and let me again just set up notations. I'll think of expanders, or the ones I'll use in this talk will be just bipartite, balanced, biregular expanders, so left and right sides with n vertices. And they will be d-regular. We'll think of d as a constant. And we'll call it a lambda expander if the second singular value of this kind of normalized bi-adjacency matrix, which will be a number between 0 and 1, is at most lambda. Again, think of lambda as an arbitrarily small constant. So d will be a growing constant depending on it. Okay. And actually, all I'll need about expanders is expander mixing lemma, which we saw last week, and which just shows that for any two sets, S on the left, T on the right, the number of edges between S and T is roughly what you would expect in a random graph, up to some error, which can be made better than this, but I'll just use a bound of lambda times the total number of edges for now. Okay. Statements okay? All right, good. So now let's get to the construction. This is actually a classical 30-year-old construction of Allen, Edmonds, and Luby, which gives a way of amplifying distance for codes. And the construction is basically some nice repackaging operations. So let me show you what it is. And so let's start with some code word Z or Z in some base code C0. We'll not need too many properties from this base code. We'll need its high rate, but the distance can be as small as you want. So the distance of C0 can be 0.00001 if you want. Okay? You don't need something very strong for it. Each symbol of this Z or Z is of size 2 to the k, where again k is, we'll think of as a constant. And now we encode every symbol using some so-called inner code, which is a constant size object. It maps k bits to d bits. D is already a constant, so this code lives in some constant dimensional space. Okay. This will need very good properties for, but we can even just kind of brute force search to find a good code. It's just a constant size object. So now every left vertex has d bits written on it. And by the way, this f2 can be fq, but I'll just keep it simple. So every vertex now has d bits written on it after it kind of encodes its symbol using this inner code. Okay. And fixing some arbitrary ordering, a global ordering on edges, we can just think of these d bits as sitting on the d edges adjacent to this left vertex. Okay. Now we can just view this from the right. So when I sort of right vertex looks at the d edges adjacent to it, or it sees d bits, it can write them down. And that will just be the code word. So every right vertex writes down the d bits it sees this way. It's just a repackaging operation. So we do this local encoding. We send the bits from the left, collect them from the right, packet them. And we think of now this f2 to the d as the alphabet size of the new code. So this right vertex has a symbol of size 2 to the d. And in particular, two code words differ on this right vertex if they differ on any of the edges. Okay. The symbol of size 2 to the d is different. Is the construction clear? So, yeah. If nothing else, I hope you remember this construction. It's just beautiful. Okay. So as I said, this is a classical construction of Allen, Edmonds, and Luby, and actually it kind of shows some sort of a local to global phenomenon for codes. It shows that if you start with this local object, this inner code Cin, which has very good parameters, then you get global objects this capital C of arbitrarily large block lengths n, which also have basically the same kind of parameters or very good matching parameters. Okay. Formally, the rate of the final code is just the product of the two rates, rate of this base code C0 and of this inner code. And the distance, and so again, we are thinking of the rate of the base code as very high, very close to 1. So it's just the rate of the inner code essentially. And the distance of the final code is again the distance of the inner code minus something small which can be made arbitrarily small by choosing lambda. So again, we're thinking of this as small. So you basically get rate Rn and distance delta n, which is the inner code, but you get it globally. And I'll prove this in a minute. But so again, this is just what I said. If you choose parameters at the rate of the outer code is very high and lambda is sufficiently small, then you get basically close to the Singleton bound or arbitrarily close to the Singleton bound for this global code. This is the AEL construction. Any questions about it? Okay. And what our result can be viewed as is just a local to global phenomenon, but for list decoding. So we can now show that if you have an inner code which satisfies this kind of average distance inequality that I just mentioned, and instead of average, let me write sums, it will be slightly easier not to have denominators. So if you take any k code words in this inner code, in this constant size code, you sum up their distances from any center x, then the distance, the sum is at least k minus 1 times 1 minus r. Okay. So if you have this kind of a property, a slight strengthening of it for this inner code, then you also have the same for the global code. Okay. So we'll prove this in a minute. But again, the constant size objects can be found by enumeration, so you can instantiate this with some inner code that if your favorite one, and you get this globally, and you get an infinite family of codes. Okay. Again, any questions? So this is what we'll try to prove now. Thank you. Yeah, it's satisfied by random codes, random linear codes even. It's and yeah, so I'll use the fact that there exist codes, and if not, you can just use folded Reed-Solomon as the inner code if you like. Okay. Sorry. Yeah, well, okay, yeah, I can black box it, sort of. My students do know algebra. I am the one who's challenged. Okay, right, good. So let's do this. And the starting point of the proof is basically the distance proof of AEL, which is a simple observation that, I mean, it's a very interesting observation that the global distances between two words x and y on the right have local lower bounds. In fact, for almost all vertices on the left, I can think of these small codes. So this time I kind of start from the right. I have x and y. They label the edges adjacent to them. I can collect these bits on the left, and then in every left vertex, I have these two little words, xl and ysl, which I'm going to call their local projections of x and y at this left vertex L. And what we can show is that for almost all left vertices, their local distances are lower bounds on the global distance. Okay? So they have witnesses, like these are witnessed almost everywhere on the left. Okay? And formally, let's say S is the set of vertices where the local distance is somewhat large, let's say theta. And we want to prove this is globally true. For people who attended the school last week, how should we do this? Thank you. Okay, I actually cheated. I told you the only thing I need about expanders is expander mixing lemma. Okay, good. So let's use expander mixing lemma. So let's look at S, where is a set of vertices with large local distance. So, and let's write down the edges where there is a distance. So every vertex has theta times d edges, where x and y, the local projections of x and y are different. Okay. Let's color them red. Let's collect the right endpoints in this set T. And every vertex in T has to have the property that x and y as the global code words are different because there is an edge where they are different. We know that. So this edge kind of witnesses the difference. And now we can just kind of upper and lower bound the number of edges using expander mixing lemma, or like the upper bound is using expander mixing lemma. And you get that if S is at least epsilon times n, if lambda is sufficiently small, then the local distance is the lower bound on the global distance. Okay? So even if 1% of vertices tell me that the distance is 0.9, it's going to be 0.9. Okay? And again, let's ignore epsilons. Let's just, for the rest of the talk, assume that local distances everywhere are lower bounds on global distances. Okay? And again, let's ignore this error epsilon in this one. It's important, but it's not conceptually useful. Okay. And this is just the statement I said by contrapositive of this, that probability that the local distance is a lower bound on the global distance is very high. It's at least 1. Okay, so let's just assume it's 1. Everybody has a lower bound on the global. Okay so far? Okay, and now we just want to prove something about distances for more than 2 things, right? So we have, let's say k equals 3. So we just want to prove that the sum of distances from x to y1, x to y2, x to y3 is at least 2 times 1 minus r or whatever. For each of these pairs, for x and y1, x and y2, x and y3, the local distances lower bound the global distances. The local code also satisfies the distance inequality. The local code we chose so that it has this generalized singleton bound-like property. So the local distances satisfy this. They are lower bounds on the global distances. So the global distances also satisfy this. Can't be that simple. So there has to be a catch. The catch is exactly what Ramprasad pointed out earlier, that we need distinct code words to apply this inequality. And even if y1, y2, y3 are kind of distinct global code words, there's no guarantee that locally their projections will not be the same. So maybe when I just look at the d edges adjacent to this particular vertex, y1 and y2 look exactly the same in those d positions. Right? And in fact, I don't even know how to rule this out everywhere. So it might not be the same 2 code words, but somewhere y1, y2 are the same, somewhere y2, y3 are the same, somewhere y3, y1 are the same, and so on. Somewhere all 3 are the same. I don't know. Right? So I can't even assume there are some vertices where there are these kind of all 3 distinct code words. So I can't apply what I just said. Even if there was 1 vertex or at least an epsilon fraction, I could have gotten away. But the key idea is that, okay, when you have these kind of collisions, we learn something a little bit. So now let's look at, let's say, the set of vertices where y1 is equal to y2. Okay? Without loss of generality, let's say this is the kind of partition we are looking at. And here, because y1 is equal to y2, any edges going out of this vertex have the property that x on that edge differs from y1 as well as y2, because they're the same. Right? And so by the same kind of expander mixing lemma, this local distance is actually not just a lower bound on the distance of x from y1 or x from y2, but on the number of positions where x differs simultaneously from y1 and from y2. Because every edge that goes out of such a vertex witnesses that x is different from y1 and x is different from y2, and so the right endpoint has this property as well. y1 and y2 need not be the same on those positions on the right, they just both differ from x. Okay. So let's call this S. These are the fraction of vertices where we have this simultaneous errors. And what we just said by this kind of local witness property, that the local distances are a lower bound on this set of simultaneous, or the fraction of simultaneous errors. Everyone okay so far? It's the same proof as the expander mixing lemma. Okay. And we also have that local distance for y3 is a lower bound for global distance. Sorry, this should have an L here. So we got that the local distance is a lower bound on simultaneous errors for 1 and 2, and for 3, we just had what we had before. Local distance are the lower bound. Okay. And now we have this S here, so let's study that a little better. So let's, for a moment, think of a code where we just kind of erase these locations. We forget about them. We keep them, the block length is still n, but we just kind of put some zeros there or some arbitrary symbols. Okay. Now for this code, the distance is still delta minus s. I mean, this s fraction we forgot about, delta was the distance, so distance is still delta minus s. And by triangle inequality in this code, okay, so first of all, what is the distance of x from y1 in this new code? It's whatever the distance was before minus s, because we erased s positions where we know they differ. Okay, same for y2. And by triangle inequality, we get this sum is at least delta minus s. Everyone okay so far? Just. But if we add this to the inequality we had before, which is this kind of this local distance inequality, you can check that s cancels, and we basically get what we were looking for, that the sum of the distances of the 3 global things is at least 2 times 1 minus r. Again, epsilons can be handled. So you get this bound that we were looking for. That basically proves the k equals 3 case. Okay. Any questions? Okay. The same idea actually extends, but let's first maybe do a little bit of a recap of what we just did. So we had 3 code words. We looked at a left vertex. This left vertex, because of collisions or whatever, induced a partition of these 3 code words. We got 1 and 2, which basically became the same, and then 3 was separate. For each piece of the partition, for each cell of the partition, we used a local inequality. We just had, after this partition, we only had 2 things, so we used a local inequality on 2 things. And on the right, we just used this kind of global inequality, which is just triangle inequality, but in the code with erasures. We just did suitable erasures. Okay, seem to have 5 minutes by my watch. Is that okay? Okay, I need 2 minutes, but okay. So on the left, we use this local inequality on each piece of the partition. On the right, we just kind of used a global inequality for things which did collapse to the same inside a partition. And then adding them just gave us the bound we wanted. And this can be extended. So in general, if you have k code words, if you look from a left vertex, some of them might collapse to 1, let's just call this A1, and some others might collapse to the same thing, let's call them A2. So you get some partition A1 to A sub P for some P parts of these k code words. Okay, I've just sort of arranged them so that the partition is easier to draw. But it's some arbitrary subsets. So we have P things now. So we can apply a distance inequality locally for P code words. Okay? But this will give us, again, errors on sort of lower bounds on simultaneous errors. So if I think of Sj as the number of positions in which X differs simultaneously from all code words in the set A sub j, this will be Sj, and again, I can define S1 to Sp similarly. So I get this local inequality for, I apply the local inequality, and then I get this lower bound for the Sjs, which are simultaneous error fractions of A1 to A sub P. And now, within every set, I apply a global inequality. But the set size might be more than 2, so I can't apply a triangle inequality. Actually, I just apply the inequality I want to prove just by induction. So now, again, I look at the set Aj, I erase the things which correspond to simultaneous errors. Okay? And then I say, if I have size of Aj many code words, if I have 10 code words, the sum of these distances should be at least 9 times the distance. And I just apply it for the erased code. I do this for every Aj. If the size of this set A sub j is strictly less than k, I can do this by induction. Okay. So the only thing I have to say is that sometimes you get a non-trivial partition. Like, it's not true that all the code words are the same on the left all the time. But that can't happen. There are code words in this base code C0. It doesn't have great distance, but it has some dignity. It's not going to let people, sort of all the code words be same all the time. And so formally, the number of partitions is at most k to the k. You have to get something non-trivial, at least on delta R0 fractions. So you get some vertices on which you get distinct code words. That's enough. Expander mixing lemma applies even if epsilon fraction of things have lower bounds. Okay. So that's actually the whole proof. And this gives you codes which hopefully are convinced that they're fairly simple construction and have optimal list size bounds. I didn't talk about algorithms. The one we have in this paper is kind of using some squares hierarchy, but Shashank will tell you a much simpler and faster algorithm. We achieved kind of list decoding capacity when the list decoding capacity is of the form 1 minus r minus r, 1 minus r minus epsilon kind of things. And this makes sense when the alphabet is, even if it's a constant, it's a somewhat large constant. So maybe what about list decoding capacity for alphabet size 5 or 3 or 2? And this is just a simple local to global transformation for list decoding, but maybe we can do this for other code properties. It seems we didn't, okay, yeah. And also, AEL kind of has a nice extension to quantum codes and so on. So can we also get optimally list decodable quantum codes, etc., using this? And so on. Okay, I'll stop here, take questions.
Thanks, Madhur, for a great talk. Any questions? And maybe Shashank can set up while.
Epsilon close is fine, right? I can add another epsilon. Yes. So you can, yeah, thank you. That's important. So yeah, it can't be exactly, I mean, it's still D, it will still be a constant, but you can do better. So yeah, it can be epsilon close to the generalizing. That will just add epsilon to the errors. Yeah. Mm-hmm. Yes. Yeah, no, It's a good question, but I don't know the answer. It's sort of, yeah, all of these do involve some kind of folding, like in Reed-Solomon or here also this bundling things on a vertex is a folding. And yeah, I don't know if that's necessary. Yeah, not here that I know of. I mean, okay, maybe there are some things to try, but I don't know how to do it yet. So yeah.
Any other questions? Maybe I have a quick question. So
Please.
because of this partition K to the K thing, so
Right.
would the alphabet size be exponentially worse than earlier counterparts? But of course you get TRS bound. So.
What do you mean by earlier? So earlier it was depending on n. So here it doesn't depend on
No, but
n.
if you do the
just
expander based things, you can get exponential.
Oh, I see. That's what you mean.
Here it will be doubly exponential.
Absolutely. So yeah, I mean, in some sense, this is not the optimal analysis. I just kind of said that I'm just going to look at one most popular partition and forget about everything else. But this analysis applies to any non-trivial partition. So maybe there's something smarter you can do. We just kind of haven't done it or sort of didn't do anything more than the trivial analysis. But yeah, it's possible that can be made polynomial.
Okay, great. Thanks again. And